This is what we did. Yeah. So this is what we did. So what are we trying to do? First, we initiate a backtrack call with index 0 and the empty subset. Then the backtrack call starting from the current index moving towards n. So that for this backtrack call, the possible solutions will be 0, 1, 2. So let's first solve start 0. So whenever you are trying to start this solution, what you are trying to do, whatever value present in this index, first you are adding to that subset. So earlier it was empty subset, you are adding the value, it becomes 1. Then what we do next, in the next step, we just initiate a backtrack call for the next index from the current index. So earlier it is 0. So we just initiate a backtrack call to the next index 1. And with the same value, we just pass it so that again the backtrack call will start from current index to n. So the current index is 1. So it will start from 1 to 2. Nice. Now let's solve one solution, then we will move on here. So again, now start equal to 1, right? So as start is 1 here because we are starting from this index. First, what we do, we add this index value to this subset. So it means whatever value you have, we added that value to the subset, it becomes 1 comma 2. Now let's move on. Now what is the next step we are doing? We have step 1, this is step 2, and we didn't write the third step, we will do that. So step 2, in step 2, what you are trying to do is you are trying to add the next recursive call, next backtrack call for index plus 1. So it is 1. So 1 plus 1, 2 with this subset. So we are calling, sorry, this is 1. So we are calling next index call. So that the backtrack call will call for 2 and 1 comma 2 subset. Now what it does again, this is the backtrack call, right? It will start from current index to less than n. So current index is 2 and n also having only n equal 3, right? It move on only less than n. So that there is only one possibility you could see, so that which is intent call 2. So it will add index 2 value to the current subset. So index 2 value is 2. So 2 is been added. Now again, it will blindly call next backtrack call to the next index. So it will for index 2 plus 1. So it is going to call for index 3. But if you closely see, if it is index 3, there is no logic. There won't be any logic executed. So that what we do, so we will just return to the caller. Okay, so we will just return to the caller. So once we return to the caller, so what we does, once we return to the caller, what we does, can you please tell me? Once we return to the caller, what we did? Yeah, why we need to remove the last element? Right. So why? Because we have caller, right? So this is being called. If you see, this is being called. Sorry, this is being called from this caller, right? So if you closely see, this start to has been started from this caller, so that whenever you are returning to the caller, you need to maintain the same original state. So what is additionally added in this caller, so which is to be removed? So then what we did now, I'm not writing it here in order to avoid that, otherwise it will make clumsy. So that what we do, we will just delete this. So generally what is happening, it should be done before this. So what we did, so for actually it should be done here. Hope you are getting it. So we are trying to delete this element. Then we are returning to the caller. Nice. So this is how it happens. Once we return to the caller, what we are trying to do, we see are there any possibilities from this caller. If you closely see from this caller, we have only one possibility. So that one possibility has been explored. So there are no other possibilities to explore. So that we are done with all possibilities of this caller. So that it's time to return to its caller. Who is calling this guy? So this one. So it's time to return to its caller. Uh, so we are just returning to this complete flow executed in the same set of instructions. So we are returning to its caller. So let's move on. Again, same thing. So whenever you are returning to the caller, whenever it means with one, if you closely see what is happening here, don't get confused. So with one, we went into next possibilities. So it has two. So all the possibilities were done with index one, so that we need to return to its caller. So we need to return to its caller. So when we are returning to its caller, again we does the same thing. Again, we does the same thing. We just remove the last element. So if you closely see, we remove the last element. Now the caller will have 1 comma empty subset, 1 comma with subset value 1. Right. So we came to the caller now. If you closely see from this caller, we have explored the possibility of starting with 1. So we didn't explore the possibility of starting with 2. So that we need to do that. So that's how the recursive call will execute. Once one possibility is explored, then it is trying to do exploration of other possibilities. So that's why initially I have written all the use cases here. So starting with 2. So let's move on. As start equal to, right, at index 2, what is the value you have? You just need to add it. So we will optimize this. First, let's understand where the flaw is. Then you can implement that. Next value is 2, right? At index 2, you have value 2. So just add value to this. Okay. So let's add value to this. So we were added. Then what we are trying to do in the same process, what we are trying to do, we are initiating the backtrack call for the next index by passing the current value, so which is 2, current subset, so which is 1 comma 2. So as the value is the current index, right? So the current index is not less than Jan. So obviously it will just simply return to the caller. So there are no possibilities to explore from this caller, so that you return to its parent. Okay, obviously you return to its parent and you just remove the last element. Now, if you closely see from this caller, we have seen all possibilities. So it's time to return to its caller. So let's return to its caller. So the caller here is this guy. Whenever you are returning to its caller, you just need to remove the last element from the list so that again it will become empty list. Now, if you closely observe what we have done, we started from index 0 and this index 0 see the possibilities of starting with 0. Now it's time to look at the possibilities of starting with 1. So let me take those things. uh, yeah. So it is starting with 1 and starting with 2. So I'm just going little quick. So first we'll add what is the value present in 1, so which is 2. Then uh, then we were trying to initiate a backtrack call for the next index, so 2 comma 2. So blindly again, this recursion, right? This recursion is going to here it is again starting with given index, whatever index it has, and it will just add that value. So our subset becomes 2 comma 2. Then it is going to try to initiate a recursive call to the next index. This is how it happens, right? So to the next index with 2 comma 2, and we understand that index 3 is out of the array size, so that we just return to the caller. So what it does, it just return to its caller, and this caller will return to its caller by just removing the last element. So again you will get the empty subset. Again, if you come here, the same process, whatever you see here, the same will be executed here. When you come here again, the same will be executed here. Hope you are following me. Let me write it little clean. So we have seen possibilities with 0. Let's also see the possibilities with 1. Then what is our job first? We will add the element 1 value to the subset. Then next what we do, so we will initiate a backtrack call to the next index by passing the current subset. And what we does, again it will start with the current index, so that start becomes 2. Then what is our job? So we'll add the current 2 value to the subset, so that at index 2 again you have value 2. So the subset is this one, so the 2 comma 2. Then we will optimize this. This is not the current solution, so I'm just exploring all possibilities. Then we will think about what is the fix we can give. Then what we do, so once we are done with it, so we are trying to initiate a backtrack call to the next index passing the current subset. And now you understand that which is reaching out of the bound, so that we just return to its caller. We just return to its caller by removing the last element, then it has the same subset. So with this, we are seeing all possibilities, then we return to its caller. By removing the last element, you again get the same subset. Now we have explored the possibilities of one. Now it's time to explore possibilities of this. Let me draw this here. Let me draw this here. So whatever here, so I'm just drawing here. So obviously you have empty subset. So you'll add value, current value. Then we move on to the next backtrack call by passing the same set subset. So anyhow, we don't have a size of 3, so which doesn't do any job. So it returns to its caller. It's returned to its caller. Then it just remove the last element and move on to the next. So that's what it happened, right? Now, can you tell me if you closely see at each level, right? At each level, we were able to figure out a subset. So this is one subset, and we also seen at each level we were able to figure out a subset. Now, can you tell me how to avoid the duplicates, right? So to make it more cleaner, this is what happened, right? So you are starting from index 0, and our backtrack call is starting from whatever so whatever indexes you are trying to pass from here, the same from that index, the backtrack call will call. And even in this case also, once you start with the current index and you will move on to the next index. So next index would be 1 and 2, and from 2 you don't have any other possibilities. From here, it could see only one possibility. It could see only one possibility, so which is 2. And similarly, from 1, it will just see only one possibility, 2. So from 2, there is no other possibility. So now, if you closely see, you are starting with empty subsets. If if you initiate a backtrack call with empty subset, then it is move on to here. So it will add a current value, and it move on to here, and to the same subset, it will add this value. It becomes 1 comma 2 because our our value is 1 2 2 2. Now again, from this subset, this will add index 2 values, becomes 1 2 2. Now again, once you are exploring all these possibilities, so I'm not once you are exploring all these possibilities, you are moving on to this end, and what you are trying to do is you are adding current value 1 comma 2, so it becomes 1, and the current value is 2. Now let's move on. So once later what you did, so you explore all possibilities. You come here, from here you again come here. So from here, so once you reach here, what you do, you will take the current value. So to this empty subset, it index 1 we have value 2, so which is been added, and it's moving to next index. So it becomes 2 comma 2. So once you explore these possibilities, then you come here. So you will add index 2 value to this empty subset. Now you have 2, right? Hope you are able to follow me. Now tell me, where is the fix we should give? So if you closely see, in this case, there are duplicate subsets, right? Here I could see duplicate subset. Here also I could see duplicate subset. How do you avoid that duplicate subset? I want to hear from you. Then do you want to explore 2 power n possibilities? Okay, you can add it as a set, but again, how do you do? So the set contains okay, list of integers, and for example, you have a larger number. It has to identify whether this list is duplicate or not. It can identify only scanning through all the elements. So it definitely, you explore 2 power n possibilities, plus you are trying to check list is duplicate or not. That is also n square if you say. So 2 power n into n square, so which is really bad. Can you tell me? Mm. Mm. Perfect, perfect. Yeah. So that's the catch here. So how do you know that, right? If you closely see, this is level one. If you can say it is level one initiated by this guy. Yes or nobody, please? Yes or nobody? This is level one initiated by this guy, right? Yes or no, please? Arey, please can you do you able to follow me? So we are trying to initiate a backtrack call from here, and which is starting from here, right? So from current 0, 1, 2. So this is in this level is initiated by this guy only, na? Yes or no? Okay, so this is level 1. And this is level 2, correct? This is level 2. Who is initiated this? Please, man. How do you get to this level? Means from here only, na? And this is level 3. How do you get to this level 3? It means from here, right? Closely understand. So this is what we did, right? So don't get confused. From 0, we are trying to initiate all these levels. From from here, we are moving on to the next levels. So don't get confused. Spend some time on it so things will be clear. Now the catch is, when do you see the duplicates, right? So when do you see the duplicates? If you see for this index one, he is the parent index, right? So for this index one, he is the parent index. Uh, okay, okay. Now I'm just making confusion here, so let me avoid that. Yeah. So when do you see that? When do you see the duplicates on the same level? Okay, so this is your level. So this is your level. On the same level, this is one level. On the same level, if the current index is greater than its parent index, so this is start, right? So you can say this is start. If the start index is greater than parent index and start index value, current index value and the previous value is same, then it's a duplicate. So how do you know that? So let's say here, uh, let's come here. Let's see, this is your current level, right? So this is the same level. When you are solving, when you are solving for index 2, when you are solving for index 2, so the index 2 is called from here, right? So the parent index is 0 for index 2. So index this start, you can say this is start and this is your parent index. Start is greater than 0, right? So it means the start is greater than the caller, and the current start value and its previous value both are same. The current start value, so current start value is 2 and its previous value also 2, then you can understand it's a duplicate. Understood what I'm trying to say? Understood, please? This is really tricky one. It's not very easy to catch it up. So what I'm trying to say, if you don't things are not clear, so just please observe. So this is your current level. This is your level. So this is actually being initiated from this caller. So when you initiate a backtrack call from 0 to empty subset, then this level is actually being initiated. So whenever this is being initiated, so check my current index is greater than caller. No. Now if you see my current index is greater than caller. Yes, one is greater than caller. My current value and previous value are same. No, it's not same, so that you can proceed with it. But when you come here, my current index is 2, which is greater than caller, and my current value is 2, previous value also 2. Then when current value, previous value same, then it is going to form a duplicate subset, so that you should not proceed further. Understood? Understood? Maithili, Banu, Ajay. Ajay, I think you already know it. Banu, did you get it? Confusing, huh? Your voice is breaking. Okay. So what are we doing here? So let me write the code so that things will be more clear. things will be more clear. So what we are trying to do, so this is our backtrack call. Once you get first problem na, it will be dead easy. Everyone without your intention, your brain will automatically think. So that's how the backtracking. So you have nums and you have index and you have a list of integers. So this is our current, and I'll also take a result. Okay, so if it is a blind call, right? Let's say uh, the traditional backtracking, how does it work? So at each flow, first you copy the result into you copy the current subset into the result. Okay, so once you copy current subset into the result, so that you can have that subset value because we are updating the current subset each and every time. Then what are we doing? So we are starting from current index, whatever caller it is calling. So this is caller, right? So the caller index, and we are moving the start towards n, and we are just incrementing it. Then what we did first we add the current start value to the subset. So you'll just add current dot add of nums of start. Then what we did, so we are moving on to the next index. I'll add the logic to remove the duplicate for now. Let's say this is our traditional backtrack, right? So we will move on to the next index by passing the, yeah, we'll move on to the next index, that is start plus one, by passing the current updated subset. So once we explore all possibilities, we just remove the whatever value we've been added. So obviously the latest backtrack call will have the value at last. So you just remove that. So it is present in current dot size minus one. Done. Now this definitely returns if I call this backtrack with the nums and index 0 and empty list. Definitely it will just solve it. You can return result, but this is returning duplicates. So if I run it, definitely it will say that you are returning duplicates. I'd say yan means nums dot length. So if you closely see, the duplicates were being returned. Now you know how to avoid the duplicates. So you know how to avoid the duplicates. So what we should do whenever, so this is what I told earlier. If you closely see, let me show it on iPad. So this is what I said here. So whenever your start, right? So this is your start is greater than the caller index. Whenever your start is greater than caller index and the current start value and previous value is same, then it is a duplicate so that you should not continue further. So that's why what you should do whenever my start is greater than caller and my current value and its previous value is same, then you just continue. So don't go further. Getting into this line number 15, right, it needs very good understanding of the recursive stack. Otherwise, you cannot, it's like you are just by hearting. So that's it. So let me run. So what is the time complexity? Tell me. Yeah, what is the problem here? Tell me, buddy. I understood. So there is a problem here. So this is not executed for this test case. Why? What is the problem? Tell me, please. Yeah, that's correct. Yeah, so what does it mean? So this logic, line number 15, right? Line number 15 will execute only when the list is sorted. Line number 15 is valid only when the list is sorted. If the list is not sorted, right? If you closely hear 4 is not equal to 1, so that it repeated that combination. So that's why you get a duplicate 4. So what you can do, so before solving this, first you sort the list. So this is much needed. So you don't know whether if the elements are already sorted, these things will work, but if elements are not sorted. So now once you sort it, it will work. That's it. So now can you tell me what is the time complexity? Please, buddy. What is the time complexity? Uh, Please. So what are we trying to do? Let's say you have all unique numbers. If you have having all unique numbers, how many subsets you can generate? If you have all unique numbers, how many subsets you can generate? Two, right? So if there are n values, then you can generate 2 power n subsets. It means you are getting 2 power n possible solutions within your complete recursive stack. So you always get to, if you see here, all or if everything is unique and all these are 2 power n subsets. So you are going to generate 2 power n recursive calls, and in each subset, right, what we are trying to do, we are trying to copy the current subset into the result. And the max size of the subset is going to be n, so that it is going to be n into 2 power n. And what is the space complexity here? So we need to talk about space complexity in two ways. One is with stack frames. Other is with actual memory. So this is our result object. So with respect to stack frames, what is the time complexity? Sorry, space complexity. What is the space complexity with respect to stack frames? How many stack frames active at any point in time? Only n, right? N, right? So what will happen? First, it will start from here, then it will go here, then it will go here, then it will go here. By the time we are moving to this track, this is already been terminated. So this will terminate by the time we move on to index 2, right? So this will already been terminated, so that at any point in time, only n stack frames gets activated. So with respect to stack frames, which is n, with respect to result, the result is holding total 2 power n subsets, right? So you can have 2 power n subset, and each subset size is at max is n, so which is going to be n into 2 power n. Hope you get this, correct? Okay, so yeah, plus n log n. This is for sort, and this is for generating the subsets. Okay, yeah, it's n log n plus big O of n. Okay, right. So let's move on. Let's solve. I think if you understand this problem, next one you can come up with the solutions. Let's see how it works. Okay, so we are done with this subset. So let's move for the permutations. Okay, yeah. So what he is trying to do, he will be given an input n. We need to generate all the permutations. So let me walk through that. Let's say you are having n equal to 1, 2, 3. So we need to generate all the permutations. So how does it work? So permutations means, you know, right? So let's say you have at index 0, 1, 2. Let me move further. So you have index 0, 1, 2. Is my voice is clear? Do you see any disturbance, or is it breaking? Everything is fine? Yeah. Actually, I have connected to my neighbor internet. There is a problem with my internet. So actually, you don't know that I'm using his internet. So I just hacked it. Okay. So this is your input. So we need to find out all the permutations. So how do you know the permutations, right? So let's say I'm starting from index 0, and this is how it is. Without getting into the logic, let's see. We want to see all the permutations. So generally, how does it work? First, you have one, two, three, right? So you have one, and once you choose element one, I have possibilities of choosing element two or element three. So let me choose. I have possibilities of choosing element two or element three. If I go this direction, so I can definitely choose only one element, so which is going to be one, two, three. So if from here, if I go this direction, I am done with one, three, so that I can choose two. Now, similarly, if I go with index two, sorry, value two, then I can choose either value one or value three. If I choose value one, I just left with three. If I choose value three, I just left with one. It means if I go this direction, then I left with three, and if I go this direction, I left with one. Let's say I start with index 3, then I can choose either index 1 or 2. And if I choose index 1, if I go in this direction, definitely I left with 2. And if I choose index 2, if I go in direction, I left with 1. So if you closely see, we have generated total 6 permutations. One is 1, 2, 3, and 1, 3, 2, and 2, 3, 1, and 2, yeah, 2, 1, 3, 2, 3, 1, and 3, 1, 2, and 3, 2, 1. So these are the possible permutations. So let me write it. So one is 1, 2, 3, and you have 1, 3, 2, and 2, 1, 3, and you have 2, 3, 1, and 3, 1, 2, and 3, 2, 1. You understood the problem statement, right? Please, I understood the problem statement. Okay, and you are giving thumbs up, so I think I'm not looking at the board. Okay, good. Right. So now, how do you come up with the solution, right? It's a backtracking solution. Tell me, how do you, with your limited knowledge, how do you come up with the solution? What is happening here? Tell me. Right. Correct. So if you closely see, this is how it is moving on, right? So initially, initially we have three possibilities. Okay. So I have three possibilities. So either I can start with index 0. So you have 1, 2, 3, right? So with 0, 1, 2. And I can start with index 0 or index 1 or index 2. Now, from here, what are the possibilities I have? If you closely see, right, this is index 0, right? If I choose 1, either I can go with 1 comma 2. But if you do in reverse direction, right? So for example, if I choose 3, I can choose 1 comma 2 here, but 1 is at index 0, 2 is at 2 is at index 1. So here you are at index 3. For example, 3 is at index 2, right? 3 is at index 2. So if I choose index value 3, I can choose either value 1 or value 2, but value 1 is at index 1, value 2, sorry, value 1 is at index 0, value 2 is at index 1. It means you don't know, right? So the order of elements is not guaranteed. In subsets, right? In subset, what is happening? Order of elements is guaranteed. It means you always pick up the next element. But when it comes to permutations, the order of elements is not guaranteed. That's why you blindly focus on all possibilities. For everything, you blindly focus on all possibilities. So what you do, again, you start with the same index, index 0, index 1, and index 2. Again, you see here from index, okay, so let me correct. So what we are doing, so we are starting from index first. Initially, we will initiate a backtrack call with index 0 and some empty list or set. What will happen? So it will go to that index 0. It will go to that index 0. It will add the value at index 0. We have value 1. Now, Again, you move on to the all possibilities, right? If you closely see, index 0 is already is already been added, so that you don't consider this. Now you will check whether the current value is present in this set or list or not. It is already present, so that you don't consider it. So once you don't consider it and you move on to the next index. So next index value is 1, so that at 1 you have 2, so that what you do, you will add 1 comma 2. Okay, so for this, that one you will add two. Now again, as you see in the possibility, again you will explore all possibilities. So which is index 0, index 1, index 2. Now if you closely see within the current recursion tree, so we have index 0, which is already added. We also added index 1, which is already been added. Now you just only left with index 2. So let's add index 2 value to this list. So once you add it, it becomes 1, 2, 3. So whenever your subset, your current object, current list or set size is equivalent to n, it means you found a permutation. You will add this into the result. You found a you found a uh, permutation, so you will just add this list into the result. So what is the base case here? What is the base case? So whenever your current list size, you can use set also, so is equivalent to n, then add to result. So this is the base case. Now what you do, again the same concept, so there is no change. The same concept, the backtrack, what it does, first it will add, then it will move on to the caller. So whenever it is moving on to the caller, it just remove the last element. Now if you closely see from this caller, we seen all possibilities, so that we are moving on to its caller. Whenever you are moving on to its caller, remove the last element, and now you have. Now if you closely see from this caller, we are done with possibilities of 0 and 1. Let's move on to possibilities of 2. So let me extend it. Hope you're following me. If you already understood the subset, it is going to be very smooth. Now you are having index 2. So first what you do, you will add index 2 value, so that index 2 you have value 1 comma 3. So 1 is already coming from caller. At index 2 you have value 3. You just add it. Now again you see all possibilities. So one is index 0, index 1, index 2. If you closely see from this caller, right? So this is coming from here to here, so that index 0 is already present, so that you ignore. Similarly, here also index 2 also present, so that because it is coming from the caller, so that you ignore. You just add the index 1 value. So you just add index 1 value to the current subset. So which is 1, 3, index 1 having value 2. So you just take that 2. And again, which is reaching the base case, right? If you closely see, this is my current list size, which is reaching the base case. So whenever it is reaching to the base case, you just add that result. That's it. Now we are done. We are just returning to the caller. We are just returning to the caller by removing the last element. Now you have from this caller, there are no other possibilities. So because we already done with this, and we are returning to its caller by removing the last element. Again, you see from this caller, we have seen all possibilities. So now we're returning to caller by removing the last element. Again, it's done with empty subset. The same process will continue. Let me quickly draw it, so that let me move this little here. So index 1, right? So now it means you're from this caller, you are done with possibilities of 0. Let's see the possibilities of 1. So same thing. So what you do, first you add index 1 value, which is 2. Now again, what are you doing? So it is blindly exploring all possibilities. So index 1 is already explored, so that you just ignore it. Now you just move on to index 0. Index 0 is a valid solution, so that first add index 0 value to this subset. So subset is 2, add index 0 value it 1. Now from here you are just exploring all three possibilities again. So index 0, index 1, and index 2. So the diagram is going a little clumsy. What I'll do, I'll just explore only this path, so that the remaining will remain the same. So I don't want to yeah, I'll just explore only this path. So you have index one. Actually, you also have index two, so that you can take it over. So what we are trying to do, yeah. So what we are trying to do, so we will just add index one value to this subset. Perfect. So we'll just add. Then what we try to do, we'll see all possibilities because the order of elements is not guaranteed. So it's time to look at all possibilities. So obviously we have seen index one, so that we don't explore this. So we will explore this. So we will add this value to the subset. So 2 comma index 0 having value 1. Now again same thing. From here again you explore. So index 0, index 1, index 2. Now if you see, this is the color we are moving on. If you closely see, we have explored index 0 and index 1, which is already present in the list. So it means index 0 and index 1 already present in the, sorry, index 0 and index 1 already present in the list. We need to move on to index 2. So the index 2 has the value, what's happening? No problem. So the index 2 having the value as 3. So just add the 3. It's got stuck. Okay. So just add that 3. So 2, 1, 3. So simply you will just add to the list. So similarly, this is also same case. I'm not drawing here, but you get it right. Everyone get it? Everyone get it? Right. So if you closely see, this is if you want to make it more cleaner. So let me write only the diagram so that adding elements is not matter. So you have starting with index 0, index 1, or index 2. For everything, you see all possibilities. So index 0, index 1, index 2. Obviously, in this path, you already have index 0, so you just ignore so that whenever you see the possibility, you explore it. So, okay, now again, we do exploration of this. So index 0, index 1, and index 2. So if you closely see in this recursive stack, 0 and 1 already explored. So this is only the valid. So that these three values will be in the list. Similarly, if you go till here, so this is how it is. Again, you have three possibilities. Index 0, index 1, and index 2. So you can ignore what are the indexes which are already been visited and you just go with index 1. Fine. So this is how the recursive stack if you start from index 0. Similarly for here, so first you see all possibilities 0, 1, and 2. So 1 is already seen so that you just ignore it. Then again you see all possibilities for this guy 0, 1, and 2. So 0 and 1 already seen so that you can see 2. Similarly for this guy 0, 1, 2, and 1 and 2 already seen so that you just consider the 0 guy. Similarly for this, let me make it little quick. Hope you get it. I don't try. I think I don't find space here. Hope you get it. So similarly for this also same use case. Now tell me, now what are you trying to do is finding a time complexity to this kind of algorithms, right? It's very tough. You need to get the time complexity from the given input. So let's say you have 1, 2, 3, and what are the permutations we generated? So you have 1, 2, 3, 1, 3, 2, and similarly 2, 1, 3, 2, 3, 1, and 3, 1, 2, and 3, 2, 1. Okay, so here n equal 3. How many permutations we got? Total permutations, how many we got? 6, right? right? So if you closely see, if I start, if my current is having one, I have one n minus one possibilities. Means I need to look for the so this is how it is, right? If I closely see, so the first element, for example, this is your elements, right? So you have element one, element two, element three, right? So you have three elements in your what do you call, in your subset, so, or in your set. Element 1 has how many possibilities? Can you please tell me element 1 has how many possibilities? Element 1 has three possibilities, right? If you closely see, if it is the first element, it can pick any one of this, right? Yes or nobody? Element 1 can be 1 or can be 2 or can be 3. Yes or no? Yes or no, bro? Correct? Element 1 can have three possibilities. What are the possibilities of element 2? No, no, no. Tell me in the counter number. This is not the value 3 possibilities. Element 2 will have how many possibilities? Yeah, you are correct only. Tell me in the counter. So this is element 2 level, right? So it has two possibilities. If you closely see at every recursive call, element 2 will take only two possibilities, right? So if you closely see here also you have two possibilities. Here also you have two possibilities. Here also you have two possibilities. Okay, so element 2 will have two possibilities. Element 3 has how many possibilities? Check here, right? If you closely see, this is your element 3 level, right? So element 3 will have how many possibilities? Please, man. One, right? Because if all two elements were, so it means it can be any combination. It can be any combination. So the element can be element 1 can be 0 or 1 or 2. So if it is 0, it has other three possible other things. Element 1 can be 1 or element 1 can be 2. So it means you have any combinations. So totally you have what? 3 into 2 into 1. So we have six permutations. If you closely see, that's what we get it. So can we write it as, if n equals 3, can we write it as n into n minus 1 into n minus 2? So is it like n factorial or not? Yes or nobody? Is it not n factorial? So it means you generated a n factorial permutations. So your recursive calls will have n factorial permutations. It means you are able to generate n factorial solutions, means you are having n factorial subproblems. So definitely the time complexity is going to be n factorial. It means you are dealing with n factorial subproblems, and each subproblem we are also copying the result, right? Yes or nobody? We are also copying the result into the result set, right? Yes or nobody, please? Once you derive a subproblem, you get a result. That result is being copied, right? Yes or no? So which is going to be n, because it means it is going to be n into n factorial. So the time complexity for this n into n factorial. And what is the space complexity, please? I think this you must tell. How many stack frames will be active at any point in time? So at any point in time, only n stack frames will be active. So what is the space we use for result? It has n factorial result, right? Yes or nobody? These are n factorial results, right? So you can, but each result will have of size n, so that it is n into n factorial. Okay. Hope you get this. So let me write the code. Can you tell me the logic? Or if you are good enough, you can post the logic in the chart. Uh, how do you write the logic? I'll wait for 2 minutes. Can you post in chat a sample pseudocode? So let me copy that. Okay, so let me do that. So what are we doing? So private void permutations. So you are going to get the given input and you are also getting the index and you are also getting the list of integer current. If you closely see, right, the size of the input at max is 6. So that's why you can use list or you can use set also, it's fine. But it doesn't maintain the order, right? So that's the problem. So I'm going with the list. Uh, okay, nice. So then what is our job now? So you are having elements. Perfect. So what we do, so what is the base case? Whenever your current, which is equal to nums dot length, it means whenever your current size, which is equal to nums dot length, it means you find out a permutation. So obviously what you can do, you can add that into result. So let me take result array list. And please solve the subset 2 problem. You also have one more problem called permutations 2. You solve it. Then, if you have time, try to solve this combination sum too. Okay, so whenever your current size is reaching the nums dot length, it means you framed a permutation. So just add that to result. New array list of. Do you really need this index? Definitely, it's not required because we always starting from zero, right? So you don't need it. So new result set of current. And what we do, we blindly always start from zero, right? So there is no point of maintaining the caller. So index less than nums dot length, index plus plus. So what we do first, we will check whether the current value, whether this current contains nums of index. So one point is all the integers are unique. So that you can blindly delay on rely on this logic. So that if the current element present in this current object, the list, so you can just move. You don't initiate anything. You will just continue. Otherwise, what you do, you will add the current element. Okay, perfect. Current dot add of nums of index. Then you will move. You will just explore these permutations by passing this nums comma current. Okay, so whenever you reach the base case, right, you will just return, so you don't do any additional thing, and you just move on to the permutations with by passing this current. Once you are done with that, you just remove the last element. That's how the backtracking works. Done. So we are done with the code. That's it. So this is our permutations. Nums comma new array list, return result. Understood, everyone? See how simple it is. So if you understand the flow, it will be easy. Otherwise it will be tough. So this is what we discussed, right? So we are blindly starting from. So this is what happening, right? If you even compare the code, this is how it works. So we blindly starting from 0 to n. So that's what we are doing. And whenever you see, so we are blindly starting from 0 to n. Perfect. Then what else we are doing? We are yeah, so we are adding current element. So we'll add the current element. Move again. We blindly start from 0 to 1. If the element is present, we'll just continue. Otherwise, we'll just proceed. So that's what we did. And finally, the base case is what? This is a base case, right? So whenever your current object length is reaching n, we are adding to that result and we are breaking that flow. That's it, because this return is very important. Otherwise, it will went into infinite. So hope you get it right.